Thank you, Phil. Thank you all. And real thanks to the organizers. This has been a remarkable piece of work that's been pulled together here. So thank you. I'm gonna walk through what I hope is a couple of things that are potentially interesting. I'll start with the gratuitous pika picture. In case you were wondering about the field trip to Rocky Mountain, this is up on Trail Ridge Road yesterday. So and there were also lots of elk farther down on Trail Ridge Road. So for what it's worth, I'm not sure what you will see on the field trip, but for Tuesday, just in case, this was up there. And we'll use the pika as long as we can. The original plan was that I would do ice and somebody else who was more important and better qualified would talk about the climate system, and there were unavoidable problems. There are a few people here like Alan Robach or Gavin Schmidt who actually know more about a couple of the things I'm going to say than I do, so if you want to chime in later, please do by all means. Michael Mann can surely do that. But what I want to do is walk through what I think are a few of the interesting things that have happened recently, and then I'll go to the ice and show you some interesting things that have happened in ice recently, and I hope we can get through with that. So, and then we'll finish up with the pika here later. So that's where we're headed for all it's worth. I want to do this one. You heard this morning, but I think it's still worthwhile to walk through it one more time. I've got a little piece of the timeline, you know, the history of global warming, Spencer's work, and you know the story. 1824 is Fourier and the greenhouse effect, and 1859 is Tyndall, and 96 Arrhenius is calculating, you know. And then I put on some new science. Right, so you know, new science compared to this is things like the quantum hypothesis from Planck, or Einstein doing relativity, or Wegener doing continental drift. And I think it's worth remembering that if you really want cutting-edge new science, you might be at the wrong meeting, okay? Because we're doing old science here, okay? And I think it is an important thing to remember. This is not a Johnny-come-lately science. The predictability of, let's say, climate science compared to plate tectonics. Plate tectonics is stinking miserable as a predictive science compared to climate science. No way it's even vaguely close. Ask any tectonophysicist, what are the odds that the Atlantic is going to break and start a new subduction zone in the next 50 million years? And see what kind of answer you get back on that one. Okay? Climate science is so far ahead of things that we take completely for granted without arguing about that it's really interesting. Okay, so at any rate, a few of the things that have come out recently. Gavin may have started this. Stefan Rahmstorf has been doing it. This paper that just came out from Frame and Stone about 2 weeks ago. There's actually been climate science done with comprehensive GCMs long enough, other modeling techniques long enough that you can start asking, were the earlier projections skillful? Did Hansen get it right? Did the IPCC get it right? And the answer is yes. Within the stated uncertainties and driven by the forcings that actually happened, what is going on in the world is more or less what was expected by the earlier climate scientists. With a couple of asterisks, Rahmstorf has made this point that in fact sea level rise has been a little bit on the rapid rise compared to expectations. But temperature rise, CO2 rise, other things going on, actually the early work is indeed proving to be skillful. And I think that's an important take home, is that this is a predictive science in the sense that if you can get the forcings right, if we actually had good social models so we knew what humans were going to do, the climate scientists can now turn that into a future with pretty high confidence. Okay. Warming is still going on. And that was, John Cook made this point yesterday, but it's worth going on that there have been a number of studies recently have looked at the question, what is going on with the temperature, what is going on with the forcings? And shown up here, the top curve is the temperature, and various versions fit to it as for what it is. This is sort of statistical modeling. And sitting below it there is the El Nino, influence, and you can see some other influences, and down the second panel from the bottom you see the human influence. And what is really, I'm going to blow this up just a little bit, what is really going on, humans are forcing warming, warming is happening, the human fingerprint is still clear in the data, and then there are other things that are also in the game, and in particular the top figure there you see, which has the global temperature, the one below it is the El Nino influence. If you put a huge amount of hot water in the middle of the Pacific, the atmosphere can't heat it up very easily. If you put a huge amount of cold water in the middle of the Pacific, the atmosphere can heat it up very easily. And so whether the heat is going mostly into the atmosphere or mostly in the ocean for the short term is fairly strongly influenced by El Nino and La Nina. And in the last decade, the system has dumped more of the heat into the oceans and less into the atmosphere. This is something that wobbles, and while you can pick out very clearly the 1998 El Nino and then the trend off of that, you'll see that this has been wobbling along in that middle panel. Ultimately, the ocean and the atmosphere have to be coupled. Ultimately, they all have to go along together. And it's simply a question of how much of the warming has already been realized in the atmosphere and how much is still to come. And so I think there's fantastic science going on the partitioning of the warming between the atmosphere and the ocean transiently. But the long-term picture, yes, heat is still accumulating in the Earth system with high confidence. No, there really hasn't been a stop in global warming. Right? And there's people have done this, so this is the Foster and Rahmsdorf version, where you go in and try to correct for these wobbles and say, if El Nino and La Nina had stayed constant, had not been a little more one way than the other, what might you have seen? And if you do that, all of a sudden the global warming signal pops out very clearly. And so is there any change in this? No, there really isn't. Okay? Where did it go? And this finally the ability to make quantitative statements about heat going into the deep ocean, the Argo floats and other advances have come just in time. I think it would be fair to say that the oceanographers would be happier with a few more floats. I think it's fair to say that this is just enough to see what's going on. But what you see going on is that a lot of heat has gotten deposited in the ocean, and it's gotten pretty far down. And so what you'll see there on the left is heat that's been deposited in the ocean, the best estimate and some uncertainties. And you'll see that bottom little bit there is that way over there is all the way down. I mean, that's really deep, and heat is getting way down in the ocean. The Southern Ocean version of that is on the right, and a lot of heat is going down in the Southern Ocean. So this new ability to observe the oceans, to say quantitatively, we see what's going on, and yes, heat is getting put in. I gave you El Nino, La Nina. There's a lot more than just El Nino, La Nina going on. And I think you will see really fantastic science on what controls this partitioning as time goes on. And it's exciting, but for what it's worth. However, right, this particular climate zombie is back in force again, that while warming continued, and I just showed you that warming continued, the global warming stopped, has had a new birth of noise. And I've been getting emails on this in the last few weeks. They were coming around earlier in the year. They were coming around last year. They were coming around. And it's just flabbergasting how what I just showed you, the science, which is, yes, the system is warming, yes, the atmosphere is warming, versus what you're hearing in a lot of the public discussion are a little decoupled. So let me do it for you. There's the Goddard Institute for Space Studies temperatures. And is it getting warmer? Yes. The confidence of this, high. If you take a long enough interval that is a statistically significant regression line, it's up. But notice how you can do this. So John said I'd be doing this, so I have to do this, right? I am born in 1957. There's the data from 1957 up to a little later, the regression line through the data, and you can see I was born at the start of a cooling trend. I married my dear wife Cindy, who's sitting back here. In 1980, we had to stay warm somehow because we got married at the start of a cooling trend, which you can see very clearly. Okay? We moved to Penn State in 1988 at the start of a cooling trend. We did have fun. We had a couple daughters. We came out here to show them the big mountains in 1997, the start of a cooling trend. They named a glacier after me in 2002, a very short, very steep cooling trend you can see there. And our daughter became a Penn Stater. She's now a science teacher, but she became a Penn Stater in 2005 at the start of a cooling trend. So my whole life, okay? Now recognize, this is right. As long as the world is variable, you can do this forever. It's really amazing. All you do is, if there's a year of rapid warming, shut up. And then you can go right back to claiming that global warming stopped until the next rapid warming, and then shut up, and then go right back to claiming that global warming stopped ad infinitum. Big fleas, little lesser fleas. Yeah, okay. So at any rate, this one is, it's out there. And be very clear, we are hearing this from the very highest levels at this point. Right? And it's nonsense, but at any rate. So this is a climate zombie. I showed you the pictures. CDC actually has zombie pictures on their website. It's really wonderful. But at any rate, this is one of the many climate zombies that are still, somebody keeps waking these things up for what it's worth. Now, you may also have heard a lot of noise recently about climate sensitivity. There's been a lot of new papers dealing on climate sensitivity. Remember the usual definition, double CO2, let the fast responding pieces of the system come into equilibrium. How much warmer is it? The lines of evidence that go into climate sensitivity, what's needed to explain the current climate? What's needed to make a model that looks like the current climate? If you take a model that looks like the current climate and you turn off the radiative effect of CO2, some of them at least may turn the Earth into a permanent snowball. You cannot have a no CO2 warming world and make anything that looks anything like the modern climate. You can, in addition, try to match the recent warming. You can try to match the last century. You can try to match the hockey stick. You can try to match the ice age. You can try to match other warm times in the past. You can look at other forcings. A volcano blocks the sun. That has a cooling influence, but that changes water vapor. And that's one of the amplifiers. It's loading on the same amplifier as CO2, so you can look at that. What you see here on the left is a whole bunch of arguments, and on the right is a blow-up of the bottom part of that, of sort of some of these lines of evidence of why we have fairly high confidence that we understand the climate sensitivity, how much warming we get out of raising CO2. You will hear a huge amount of noise of people who pick out one study, one line, one piece, without dealing with the whole body of evidence. And the whole body of evidence is fairly clear on this, that there is notable warming that you get from CO2. Now, what happened last year, late in the year, the PaleoSense community, a whole bunch of people got together and said, let's try to do the best job we can of summarizing and pulling together the history, the older parts. The younger parts are in good shape, the models are in good shape, and what have you. This is looking primarily at things that go way back. Can we match the last 500 million years? Can we match the Ice Age? Can we match the Pliocene? Can we match the Cretaceous, things going on in deep time? And this one happens to be done in watts per meter per Kelvin, but if you look at the distributions on the right, the vertical bar at the peak of the distribution is 3 Celsius from doubled CO2. It's 2.9 and 3.2 or something like that on the two of them. So it is essentially 3 Celsius from doubled CO2. They get essentially the same answer as everyone's been getting all the time by pulling together the full suite of paleoclimate evidence. Okay? But this is worth pointing out. If I blow that up, and then I ask which one of these, this particular paper, when it came out, I don't remember any journalists calling me or any bloggers calling me, maybe one, but there's just almost no interest in this particular paper summarizing this vast body of research when it came out. But there was one paper that fed into this that I spent 2 or 3 days on because everyone called. And lots of bloggers, and lots of reporters, and people in government, and people in the security apparatus, and what have you. I spent some number of days talking to people about one of the dots on that plot. And you can probably guess which dot it was. It's the lowest one. And when that one study came out, all of a sudden everybody was really excited. Haven't you scientists been overhyping this? And it dominated my time for quite a while. And I can tell you, we could sit down and talk about that particular study and why it's fairly clear to a lot of us that it's a lowball estimate. It was a very careful study, and you can go through and look at it and see why it came up lower than the others for good reasons, and why the answer probably is higher than that. But the press and the bloggers and what have you got very excited about just one. Right? Okay. So then I want to bop off, and I was supposed to be doing physical climate or climate, but I'm going to sneak a little bit of biology in here. I hope the organizers will forgive me. Because there's been a really interesting science on this. And I think in terms of what matters coming out of climate science for real people, what we've been learning recently in some of these issues is maybe the most important thing. So what is shown on here are statistical fits to crop yields. And the crops along the top there are corn and soybeans and cotton. You can do this for other ones. And the bottom axis on each panel is temperature, basically. And so what this is actually is looking what happens to your crop if you get a really hot day, or you get a few really hot days. What happens to the yield? And the vertical axis there is actually a log scale. You can't see that very clearly from the back, but it's a log scale. And what you'll notice is as you go to warmer temperatures, not much is happening, and then it sort of goes in the toilet. A lot of the things that we eat, that we use, that we grow, if you give them enough water, enough fertilizer, you give them space, you give them sunshine, you keep the bugs off, you keep the pests away. If the hot day of summer is too hot, they don't grow well. And it doesn't take many hot days to cause a real problem for the crop. And what you see there is statistical analysis of the crop yield data. And in the bottom in green is where the data came from. So we actually are growing crops at hot temperatures that they get unhappy and they don't yield very well. Okay? Now, this one is maybe even harder to see, and I'm going to blow up a panel in the next picture and talk through it a little more. This is a fairly complicated thing from LaBelle and co-workers that came out last year. And what you have is growing season temperature, average growing season temperature on the bottom, and the log of crop yield going up. And each dot is a country. And a big dot means a country that grows a lot of that crop. And a little dot means a country that grows a little of that crop. And what you'll notice is as you drift over to higher temperatures, the dots on how much yield they got go down. As you go to higher temperatures, it goes down. And let me blow this up a little more here. So this one just happens to be zoomed in. And what you'll see, if you go in the field, and you go in the lab, you go in the greenhouse and grow things and ask what temperature do they like, that's the gray bar is the optimum. And what you'll notice is as you go past that gray bar, the experience in the field, in the real world, is that the hot places are having lower yields. Okay. And a whole lot of what we're growing is on the warm side of that optimum for some of these crops that we care a good bit about. And so this happens to be, you'll see maize and rice, corn and rice there. But this is potentially very, very interesting. Okay, and this is real-world behavior. Is it possible that there is adaptation to be done, better seeds and what have you? Almost certainly yes, but this is real-world behavior by real people out there growing, and you'll see something that's interesting there. Okay, this one from Battisti and it was Battisti and Naylor, I think. Yeah, Battisti and Naylor, 2009. They looked at fairly rapid CO2 release scenarios, and what they ask is, what is the probability that late in this century, the average summer is warmer than the hottest one seen up to 2006 in the instrumental record. And the red down there is more than 90% probability that the average summer will be hotter than the hottest one on record. Now, if the summers that we have now in hotter places are correlated with low yields, and the summers that we have now, the hottest ones seen are going to be below average by late in the century, that's relevant. Okay. This one also just came out, so this is done, Stouffer and John, 2013, in Nature Climate Change. You know that if it's too hot, you're not supposed to go practice football outside, and if it's too hot, and if you get locked in a sauna and it's too hot, you die at some point. There are limits to what can be done. And so this one looked at, what does heat do to the ability to work outside? And what you'll see there is for the worst month on a rapid rise, burn everything and we can get our hands on and crank the CO2 into the air trajectory, what you'll see is averaged across the globe's people, somewhere where you lose the ability to do 40% of the outside work in the hot month. Now, that's averaged across all the world's people, so that includes a lot of people who live in cold places who are probably still working outside. People who live in really hot places, you're starting to get into real trouble if we crank temperatures like that. And the other paper that went with that one, this is not a projection. This is not the answer. This is within the realm of possibilities that we could, in a burn-it-all future, if we're really good at finding fossil fuels and the sensitivity's a little high, make it too hot for an unprotected person to live in parts of the world. And this was published in Proceedings National Academy in 2010. Like I say, this is not this will happen, we're doomed, it's all over, but within the realm. If you wanted to say what's still in the scientific possibilities, this one is sitting out there, that you make it too hot to work outside because you're going to die. Okay? Now, there's one other one. Bill Nordhaus, a few years ago, tried to do aggregation of economic data. There are many ways you can go after the influence of climate on economic activity. All of them are arguable. And I'm not an economist, okay? But Bill's pretty good. He's pretty well recognized. And he's got two plots up here. The one of them is per person, and the other one is per area economic output against temperature. And if you go to people who live way at high latitudes, they tend to be very sparsely settled, but they have a lot of economic activity. And the people at low latitudes where it's hot have less economic activity. And what this one shows is per person, the hotter it is, the less economic activity per person. Per area, there's an optimum in the middle. And if it gets warmer than that optimum, then economic activity goes down. And he tried very, very hard to control for the sorts of things you'd worry about, like colonial history. And look, he's comparing things within countries and within political and so on. And the world is a little on the warm side already. And so what would come out of this then is essentially the social price of carbon. If you turn up more, you're turning temperature up, and you're moving in a direction that statistically now is associated with less economic activity. Okay. There may be some stuff bears on this from the past. So if you remember, late 1700s, early 1800s, the geologists of the UK, the geologists of Western Europe and other places are trying to learn how to talk about geology. And they want to break up that vast history that they didn't know how vast it was into chunks that they could name. And so they're sitting here saying, this is the Cambrian, and this is the Paleozoic, and this is the Mesozoic, and they're drawing lines across geologic time and giving names to them. And what has turned out since then is that they were remarkably good. And the lines that they drew, which were usually based on extinction of something, have proven to be really key things. They identified the big events back in the late 1700s and early 1800s. One of those events is a meteorite that killed the dinosaurs. And Alan talked about that earlier. That's the only one that we can confidently trace to a meteorite. A few of those events, and maybe more of them, are linked to climate. And so what is coming out, and if you go through the whole thing, what you find is that CO2 has been really big in that climate story when it's going on. And the warmings are the ones that are best nailed right now. So if you may remember the end Permian, the end of the Paleozoic, the start of the Mesozoic, roughly 95% of the species known from fossils become extinct. You can fuzz that number a little bit, but not very far. And it happens to be the time of the greatest outpouring of volcanism that we know of on the planet in the history that we've got well record. Now, you may recall, if you turn on volcanoes, volcanoes are like industry. Right after World War II, you crank on industry, it starts putting up particles, it starts putting up CO2. The particles fall down in a week or two. The CO2 stays up a lot longer. What's the effect of industry? A little bit of cooling and then a warming. If you turn up volcanoes, what's the effect? They're blocking the sun, but they're putting up CO2, a little bit of cooling, and then a warming. This is a long-term volcanoes, maybe 500,000 years, maybe longer. And so you're putting up a lot of CO2 over time. The Earth got hot. It also seems to have had no oxygen to speak of in parts of the ocean. There are biomarkers of green sulfur bacteria that photosynthesize with H2S in their system in the surface ocean. So that it seems like there's hydrogen sulfide coming out of a euxinic ocean. But it's pretty clear you turned up CO2 and it got hot, and then CO2 plus fertilizer led to really bad dead zones in the ocean, and then most of the things on the planet died. And that's a very interesting thing. This next plot is very, very hard to read from the back. I just copied this out of a great piece in Science. This is still one paper. It's not the assessed of the National Academy or anything. But right after that time, in the early Triassic, it was hot. And there's some curves wandering across here that you can just barely see from the back. And there's a red bar that says too hot. Too hot for marine animals. They basically get in trouble at that point, and the plants get in trouble along there too. And so it does look like, with a high CO2 world in the past, that it was hot to live in the tropics. And this particular plot shows where the big fossils are from in the ocean and on land in that really hot time. And what you'll notice is, aside from some sitting there on the west coast of North America where there might have been a little upwelling, and other than that, what you'll notice is a bar across the middle where they don't seem to find big fossils. You will hear more about this. This is not the CO2 is a greenhouse gas pound on the table near certainty. This is still an evolving story, but it's a story that looks like when you turn CO2 way up, big changes happened and a lot of things died. And this idea that you might make the tropics so hot that it's difficult for big critters, there is at least some support for this in the paleoclimatic record. Okay. Now, I'm going to do a little bit of ice stuff. So this is the record of sea level. Sea level is rising, and it's running along at something like 3 millimeters a year. You'll see that little dip on the end, which is water storage on land related to El Nino and La Nina. I spent a fair amount of time answering questions on that down dip. I have spent much less time answering questions on the up dip. That was another one of these climate zombies. But sea level rise is going on, and it's going on in part that the sea level is going up because the ice sheets are going down. And if you caught this, they got all the different groups together that are doing the different techniques, doing ice sheet changes, and they are seeing that some part of that sea level rise is coming from the ice sheets. The rest is thermal expansion and melting of mountain glaciers, maybe a little groundwater depletion as well. The technical virtuosity of this is flabbergasting. The ice sheets can raise sea level more than 60 meters. The contribution measured here accurately is 0.6 millimeters a year. So 0.6 millimeters a year out of 60 meters of reservoir, they're measuring the change. That is the equivalent of me gaining or losing a third of a potato chip in a year. And if you can sit across the room and measure that, you could be a glaciologist. At any rate, okay, for what it's worth. A few things to keep in mind. The press got really excited by this story. This is not the big story, but it's a wonderful story, and there was some really good reporting on this by some really good reporters, and also some breathless reporting in various places. The edge of Greenland has big lakes on top of it. And those big lakes really do wedge open cracks, and when they do, they drain through. And so here's Sarah Doss. After the lake drained, it was doing twice Niagara into the ice sheet for an hour. And thank goodness Ian and Sarah were not on the lake in their boat when it did it. But that is not the end of the world for Greenland. And the reason is Greenland sits on really big, gnarly bumps in the bedrock. And even making the bottom slippery, it can't fall in the ocean. And that's reassuring. Greenland cannot fall in the ocean if you just make the bottom slippery. And so people looking at Greenland, too hot and it melts. And that's in the time scale, centuries, millennium, but not next week. And that's pretty clear. Okay. Let me, though, poke you down to Antarctica. So I had a gratuitous pika picture. We have to have a gratuitous penguin picture. And so here's a gratuitous penguin picture. Cindy and I were down in Antarctica with the GSA in January. And here are a whole bunch of penguins keeping their feet cool. And a whole bunch of penguins keeping their feet cool. And they're keeping their feet cool. I'm standing on the tip of the glacier here, Haney Glacier. And the glacier was down where the yellow arrow is not that long ago. This is a region where there's a lot of warming going on, and we're seeing the little glaciers and other things melt because the warming is happening. And that's fairly clear. And that leads us to something if we go farther south. So this one ends on land. You make it hotter and it melts. It's not listening to the ocean except through the atmosphere. Farther south, though, we're going to see that they do listen to the ocean. And so, as you probably know, if you make a pile of anything, it tends to spread under its own weight. The Gothic cathedrals tended to have the roofs cave in and the walls bulge out until they invented flying buttresses. The pile that is the Antarctic ice sheet gets down to the ocean, and it has flying buttresses, which we call ice shelves. And they flow over the ocean. They run aground on little high spots in the bed. They sit in bays and have friction on the sides. And those flying buttresses are down at low elevation where warming can get to them. And so what we're going to do here, this is a picture. Most of you have seen this, but it's worth, I think, walking through once again. This is a satellite picture, and it's up there in the Antarctic Peninsula. The peninsula is up on the upper left, and the ocean is out on the right. And that Larsen B in the middle is the flying buttress. It's a floating extension. There's friction on the sides of it. And in this picture from January of 2002, it has lakes on top of it. Now remember what happened in Greenland. The lake breaks through, and the ice does not fall off completely because there's big gnarly bumps underneath. Here, there's lakes on top. If they break through, there's no big gnarly bumps underneath. It's ocean. And so what I'm going to do for you is make the labels go away, and then I'll make the ice shelf go away. And you can watch it go away. This is 5 weeks. And it went away. And that blue slushy in there, you'd paddle your kayak through. That's just ground up ice. And after this, the glaciers flowing into it from above sped up as much as 7 or 8-fold. So they no longer have the friction on the sides of the flying buttress to hold them back. They're free to go faster. Now, fortunately, there's very little ice behind this one. But there's lots more places that have flying buttresses with lots more ice behind them. And so that's what we're spending most of our time on these days, is trying to understand that particular system. Okay, now if we go back to Greenland, this is nice, gnarly bedrock, but if you look in along the yellow arrow, you see the fjord of Jakobshavn ice spray. And if you fly up there, I showed this picture last night, you go over the seal, and eventually you get up where the icebergs break off and the ice is no longer broken up as much. And if you imagine that you self is the smiley face, the next picture is the orientation of the smiley face. And you're looking down on the ice. When the ice was out where it is in 1992, this was sort of the fastest glacier on the planet. And then its flying buttress, its ice shelf broke up, and it retreated. It still is retreating. And when it lost its flying buttress, it between doubled and tripled its speed from what had been sort of the fastest glacier on the planet. And so the warmer water attacks in various places, but it seems to have the same effect. You weaken the flying buttresses, they break up, the ice goes faster. And the faster flow of the non-floating ice to make it float raises sea level. Now, what did this? These are temperature profiles in the ocean off the front where you could get a thermometer in there, just off the front of this thing. The blue is when there was a flying buttress and the ice was happy. The red is when the flying buttress broke up and the ice was unhappy. And the difference is 1 degree in the ocean. So 1 degree ocean warming, which may have been us, may have been winds, may have been a bunch of things, takes out the flying buttress, the ice goes a lot faster. Okay? So if we go back to Antarctica, everything in color in this picture can dump icebergs and potentially respond to ocean warming taking out its flying buttresses. And if we zoom in on this little piece right here, we're going to go in the little box in this zoomed in piece because that's the most interesting one. And this is a picture of flow speed. Black is really screaming fast and blue is really slow. The black one coming down from above is sort of stuck in a bedrock trough. It can go faster, but it has troubles really running away because it's got sort of gnarly bedrock. The black one at the bottom doesn't. And that's the one we're most interested in right now, because what you'll notice is that fast velocity goes way inland and it sort of spreads out a whole lot. And it's sort of funneled down into that little black thing at the end. And if we look at the bed, this is a perspective view, and I'm just going to go ahead and put the arrows in the way. So if you think about the ice screaming into that black one there, it is screaming in along these red arrows. And the blue is well over a mile below sea level, but it's got a whole lot of ice above sea level. And take a look at this picture. Notice the merge coming in from the right. Where there's a merge, traffic backs up. Well, this particular place, there's a merge both ways. It's merging from the sides, and it's also merging vertically. And if it backs up out of the mouth of where it is, it goes into unmerged. It goes into deeper, it goes into wider, it goes into potentially much faster. And this one is one of these, I would dearly love to be able to tell you it is stable where it is. I would dearly love to be able to tell you what we know with detail. A bunch of modelers, including Byron Perzak, working with us, just published a paper in JGR. They took what we don't know about that merge, and they put it into a model. And on one end of the uncertainties, that thing sits there for a millennium and there's no worries. And on the other end of the uncertainties, there's a lot of worries. And that's sort of all I can tell you right now, aside from that's real. Then I'll finish with just a couple of thoughts. If you happen to see our TV shows that Jeff and Ern have made, the military has sort of gotten the business that these changes in food, these changes in sea level, these changes in other things matter. So the Quadrennial Defense Review said, hey, climate change is a big deal. If you missed it, Navy Admiral Locklear was up in Boston in March at a security meeting, and he was chatting with the Boston Globe. He's the Pacific Fleet. He has to worry what's coming out of North Korea. He has to worry whether Russia is going to get along with China and Japan over various islands in various places. And they said, what are you worried about? And he said, oh, the warming climate. All right, so let me walk you through the end. If you remember the glowing embers plot, past warming, future warming, what are you worried about? Redder is more worries. If you blow that up and take the warming so far, there's winners and losers. The first degree didn't cost much. Shall we try another one? And at some point, as you get away from that optimum, we can still grow the crops we have sort of in the places they live, and you go to that plunge off the edge. As you get a lot of warming and the ice is in a very different world, what do you get? Costs going up faster than temperature. Projections out to 2050 don't look that scary. Projections out to 2100, I think, scare a lot of people, to be honest, on things like food and ice stability and what have you. And so what I shut up about then, climate science remains robust, okay? I don't see any serious reason to change sensitivity. I don't see any serious reason to change projected warming. Impacts to 2050 don't look that big. Impacts beyond 2050 can look really big. And given how long our energy system lasts and how hard it is to turn, we're probably most of the way to the 2050 already. We've sort of locked in most of that. And so what you get, and as I said last night, and I'm going to say it again every chance I get, if you put the full suite of scholarship on all of this in, it says that ignoring this versus dealing with this, giving the science a seat at the table with what we care about, what we believe in, and where we want to go, ends up with a better economy, with more jobs, with greater national security, with a cleaner environment, with insurance against catastrophes, and more consistent with the golden rule. And it probably is a lot happier for Picus, too. So thank you.